Good evening, good afternoon, and good morning from wherever you're joining us from today. My name's Sarah and I'm the Program and Event Manager at the Reactor in Sydney, Australia. Welcome to a Microsoft Reactor Sydney live stream event. Tonight I would like to welcome back Stefano Tempesta. Stefano works at Microsoft in the Azure Confidential Computing product group to make the cloud a more secure place for your data and apps. Additionally, as advisor to the Department of Industry Australia on the National Blockchain Roadmap. His current focus is on helping people gain and own their digital identity with specific attention to the education sector. This evening, he'll be demonstrating how to protect your financial ML workloads with confidential computing. This session will be 60 minutes with about 10 minutes for questions at the end. And however, do send your questions throughout and Stefano and myself will be able to answer as many as possible. At the conclusion of this session, we'll also share with you a link to the feedback survey in the Q&A section. And this will be uploaded to YouTube in the next 24 to 48 hours on the Microsoft Reactor YouTube channel. So if there's anything you missed from today, you can refer back to that and we will share that link. But for now, I'd like to hand the floor over to Stefano to begin. So Stefano, over to you.
Hello, everybody. Thanks, Sarah, for the beautiful introduction. And yes, so tonight I'm following up on another Reactor session that I had a couple of months ago, where I sort of introduced confidential computing. Today, I want to go a little bit more in detail into some very specific use cases in the financial industry with attention to machine learning, because they really fit well into confidential computing. So quick recap, if you remember, confidential computing is all about protecting data and application when running in memory, when are in use. So not encryption of data at rest, not encryption in transit, but is encryption of data when it's actually being used in memory. And that is essential for protecting your confidential data, because if someone try to attack your application, your virtual machine, your container when your application is running, well, they can take a memory dump, for example, they can steal your data. That's not nice, right? So we want to protect that memory space by removing the access to this enclave, as it is called, and storing confidential data and application inside this enclave. So today I'm going to go through some use cases where this enclave, which is this memory space that is completely protected, where your, in this case, machine learning application is running, is used for some financial workloads for online payment fraud detection and credit risk prediction. Now, there is an extension to the traditional machine learning that you may be familiar with, which is loading your data, training your model, and then exposing this as a web service, which I'm going to show you in a moment when talking about the two use cases identified for tonight. This additional model is called Federated Learning. I don't want to spoil it now. Let's go in order, topic by topic. As we go through this, please type your questions in the Q&A. I will pause at the end of each section, grab the list of questions, and then try to answer as many as I can. And then obviously we'll have a little bit more time at the end. So said that, let's start and do online payment fraud detection first. And I want to draw your attention on this list of transactions. Some made up transactions. If you see, there are in different dates. There is one single client, is always the same person, Mike Randall. He bought a few different products in different places, mainly Ireland. So I can suppose that he lives in Ireland. And then there is one transaction that is a little bit out of the typical type of expenses that he does. Can you spot it? In 3, 2, 1. All right, I'm pretty sure that you have identified that Mike Randall allegedly has spent 2,000 euros in a transaction in electronics in Kazakhstan. And it's not too much about the place, but it's more about the amount that strikes out of the average. Because all the other amounts, if you notice, Mike doesn't spend more than 200 euros or 230 euros. Then suddenly he bought something for 2,000 euros. It may be legit, maybe not. We don't know. It's an anomaly, and we capture as an anomaly. Now let's have a look into this other list. Again, a list of transactions, different people, all buying from Amazon. Again, all from Ireland. And if we look into the amount column, it seems quite ordinary, not big money, right? So some euros between 30 to 300 euros, quite average. But if you spot the anomaly, we have Johnny McTick buying something, not for a lot of money, but on the same date, the 22nd of April, in Ireland and in Nigeria. So unless you took a flight from Dublin to Laos, I believe, in Nigeria on the same day, then it's very unlikely that it could buy from not two countries that are really far away from each other. Now, what's going on in there? There are some anomalies. And how did we spot this? With some scanning, visual scanning of this spreadsheet. 50 transactions on the left, 50 transactions in the middle, easy to find them. Only Visa, the credit card, handles 2,000 transactions per second. That is 170 million transactions per day. Now, good luck opening 170 million transactions in an Excel spreadsheet and going through all the lists and find the anomaly. And I don't have to justify this. I don't have to tell you how this is important, but fraud for the digital economy accounts for over $5 trillion US per year. This was a study of 2019, probably, yes. So that's a big deal. Now, why this is still happening? Well, it's still happening because a lot of the institutes like Visa, MasterCard, PayPal, all the banks, they're still very, very traditional in the way they try to detect payment fraud detection. They analyze transactions a little bit as we've done with a human review suspicious case. So they use a little bit of horizon scanning as we have done before, looking into the list. Oh, let me see, a little bit of gut feeling, and they maintain some risk tables, manually maintained, which means that, say, there is an outbreak of password leaks or credit card number leaks in some country or in some service, then we add the security director at the bank will add that vendor or that country to the blacklist, and then the logic that analyze all these transactions will put an alert on that. Now, obviously, you need to update this risk score regularly to keep it up to date in order to prevent false positive. What's a better approach? A better approach is to use machine learning, to use technology for doing this on our behalf. Machine learning works on the basis of large historical data set. Data set that have been created using a collection of data across many clients, many industries. And now the beauty of this, that even companies that only process a relatively small number of transactions are able to take the full advantage of the data set for their vertical. So allowing them to get accurate decisions on each transaction. And now not only the increased transaction, but these models also learn or self-learn automatically. So the risk table that we have identified before, that is maintained manually, is actually updated as transaction happens automatically by the system itself. So just to visualize how anomaly detection works, so I'm speaking of anomaly detection, if you didn't get from the beginning. So anomaly detection is a branch of machine learning that basically try to identify a cluster of average similar transaction, in this case, in a very easy way, on two axes. On the horizontal axis, we put the average purchases per week in dollars, and on the vertical axis, the how many purchases have been processed this week. And then you can see there is a sort of a cluster that maintains the sort of consistency. And suddenly there is one transaction that is out of this aggregation. That's the anomaly. Now, it doesn't mean that is necessarily a fraudulent transaction, but certainly it may require some additional investigation. It can be put on hold unless you do a multi-factor authentication. For example, receive a PIN code on your phone to authorize the transaction, or receive an email with a code to authorize the transaction. Sometimes even receive a call from your bank. It happened to me that I was overseas. I didn't inform my bank that I went overseas, and they find out that I was spending money. And you know what? I was in Italy, and I was using my Australian credit card in Italy, and they even call me and they say, we have noticed some transactions happening in Italy. And they say, well, yes, I'm here. Oh, you didn't tell us. Anyway, so you get the idea how this happens now, and how machine learning can help in automating this process. It does, machine learning does it using a capability called feature engineering, which basically looks into all the different variables that are considered in analyzing a transaction. Location, I mentioned, but also mismatch between the shipping country, the billing country, IP address that have been put into a risk table, the average transaction that you've done in the last month or 3 months or year. So all these different variables that are called features, and they are engineered, so they are analyzed and to identify patterns and anomalies. So anomaly detection is a branch of machine learning which is used in a lot of different situations, not just for this payment analysis. Is used for in general identifying patterns and anomalies in those patterns. And I can think of, for example, in the healthcare for patient developing a disease or something around network intrusions, checking values into for testing automation in a system, in a software, and identify anomalies. There are different use cases, but for today, let's focus on this financial use case of payment, fraudulent payment detection. This can be done in two ways. One with unsupervised learning, which basically is a way to say, you know what, dear machine learning service, I don't know what kind of data I'm getting in input, so I can't label it. I can't say that this person spent that much money on a monthly basis. You find out. And the way machine learning can find out these patterns is running a Pca anomaly detection, where Pca stands for principal component analysis. So it's the service, the machine learning service, is looking for the principal components. So it's doing an analysis of all the data in input and finding the principal components that define the patterns to identify in the data source and for which the anomaly may be detected. But if I work with a data set that I have a little bit of better knowledge and I can label it, so I can assign a precise value or a tag to each field, then I can do a supervised learning. In that case, there is another approach which is called one class support vector machine, and the name basically defines a single class whether this transaction is fraudulent or not, is a yes, no. Now, the way this is done, this is an example of building a anomaly detection in Azure Machine Learning. So I want to go in Azure Machine Learning Studio and show this in action. First of all, you want to sign in into this website, studio.azureml.net. And from here, you have access to Azure Machine Learning Studio. There are two experiences that you can have. This one is the classic experience, where you can sign up completely for free, nothing required. I'm actually using a free account, and it can be even anonymous. Completely anonymous as a guest workspace. You have 8 hours to play around, and then at the end, everything is destroyed. Or, as in my case, I'm paying the incredible amount of $0 per month to have a free workspace with 10 gigabytes of storage. So I can store my dataset and my machine learning services, as I will show you in a moment. And it's a free access that never expires. Obviously, if you want to scale to production workloads, enterprise level, there is a standard workspace that comes with a subscription fee. But for now, I'm just signing in with my free account, and I can go and show you, the list of experiments that I have built, and I have many. Okay, so I play a lot with machine learning. So for today, I'm going to show you the online payment fraud detection. Online payment fraud detection is a flow that is defined in typically 3 main blocks. The first one is define the data that you're dealing with. So we start with payment data, and I can just visualize the data set, and I can show you timestamp, the client, description, country, and amount spent. Okay. Then I'm applying some transformation. Then the second step is splitting this data between a portion that is used for training, so to create a train model. In this case, using a one class support vector machine, because I actually know the label of my field. And then the third part of the experiment is to scoring. And the scoring defines, as we go visualize in a moment, defines the probability that a transaction is genuine or fraudulent. So once I publish, I define this service, I can publish it as a web service. Let me see, so this, here we go. I can publish as a predictive experiment. And what Azure Machine Learning Studio does is that it publishes it as a web service, as a REST API, which is available in here. There is no infrastructure for you to configure. Everything is done for you, hosted as a service in the Azure cloud. So if I open the service, you can see that I can consume this service with a post. You see, this is a unique URL that is assigned to my service. I need to pass a API key in the HTTP header, and this is for authentication purposes. This is my service. I don't want anybody else to consume it. And then I pass a request as a JSON file, as a payload in the request that contains the client, country, amount, and the date of creation. And then in output, I received the probability that a transaction is true or false. So if I go in here, and just test, so I can test in here. I can just type something like Stefano in Australia and spending $200 today, which I believe is, what is today? The 6th of May, 0506. Okay. All right. So if I go in here, now I should get a score. Here we go, which is down here, which is very low score. Okay, so it's 8%, so 0.08, so 8% likelihood that my transaction is a fraud. If I change the amount and I type exactly the same condition, So Stefano, Australia, but I'm gonna put now, I don't know, 10,000, okay? Let's make it big. And the same date. Here we go. I get a much higher score. Actually, this is not in percentage. It has to be normalized to something. Anyway, I'm getting a much higher value, and this value is defined that a transaction is potentially fraudulent. Not only I see this from the score, but I also see from the label. Okay, so 0 means not likely, 1 means likely, and this is the one class vector. So is one class, 0 and 1. If I wanted to have multiple options, then I will use a 2 class or a multiple class vector to identify everything in between. But in this case, is either is fraudulent or not. Then obviously it may not be, because I'm actually buying something for $10,000, but at least the system identifies an anomaly in the cluster. All right. Any question on this first use case of anomaly detection? Let me go and check the chat. No question. Okay. And if you want to learn more, I will share my contact details at the end, and happy to share the code for implementing this anomaly detection in Azure Machine Learning Studio. Everything is open source. All right, then. So let's move with the second use case, which is credit risk prediction. I'm going to use existing data set, which is open source, is available at the URL that you see on screen here, and is a collection of credit card transactions from Germany, which was published by some university. This data set contains 1,000 transactions. 700 are low credit risk transaction or users, and 300 are high risk. What do we want to achieve from this? Sorry, I said credit card. This is not credit card. This is a transaction for credit risk assessment. So what we want to achieve? We want to identify whether a person that is applying for credit is at risk or not to be able to repay for the amount they borrow. So again, is a 2 class, low risk and high risk, and we want to assess this based on a number of variables. There are 20 variables that identify whether a person is of one class or the other one. Now, this is not anomaly detection. This is a classification, and this classification basically identify the 2 classes. Let me go a little bit quicker on this because I prefer to show you in the system in machine learning. But the way it works, basically, it creates a decision tree. This is why it's called a 2-class boosted decision tree, which basically takes the first variable, the first feature, say employed or not, and analyze the majority of people that are employed in the historical data set are low risk than the other one that are not. And then it goes into the second branch or the second question. And then the second question can be male, so gender, male or female. And then it carry on with another question. Age is in between 20 and 30, 30 and 40, 40 and 50 years old, and so on. And then I don't know, some other things like owning a house owner, landlord or not, and so on and so on and so on. So it's a decision tree. The system stops at each question, each variable. Based on the historical data set, the majority of people that are in this class are more likely to be a good repayer, and the other one are not, until it gets to the very end and then defines the class where a person belongs as a low risk or a high risk. Now, typically, this process is not that obvious, so there are different ways of doing it, and Machine Learning Studio creates the condition for evaluate 2 models, 2 approaches, and see which one perform the best. So before, for the online payment fraud detection, I said that there are 3 key steps, which is in defining a machine learning service. Get your data, split your data between training and test, and then score it. Now there is a 4th step, which I'm going to show you in a moment, which is the evaluation. Evaluation of the models between the one that has been scored with one approach, with one machine learning approach, and the other one that is to compare. So this is how it looks a little bit more complex. So we have the German credit card. I don't think it's credit card. It's German credit data without card. German credit data in there. Split the data, train the model, score the model, and then evaluate at the end. Okay. So again, let's go in the system. Go to my list of experiment. Which one I'm gonna take now? Wine sommelier? No, we're not talking about wine. We are talking about credit risk prediction. Yes, it is. Okay, credit risk prediction is in here. So German credit card. Let me show you this. This is a data set that I said is open source. I downloaded from the website. It contains different columns, different features. How many? 20 columns. And the last one is 1 low risk, 2 high risk. 1 low risk, 2 high risk. Okay. Now, how do I know that? Well, that's a good question. I could go here on the website where I downloaded this data. Okay. And I can see that there are all the different attributes. Column 11, 12, 14, different columns, different attributes. So it's all described in there. So if we go back one more time here, so we will see we don't have a clear value. Like this one can be, I don't know, male and female, for example, right? Or maybe not. Let me see which one. This is attribute 9 is gender and status. So attribute 9 is, actually, I was right. Column 9 is this value here. Then if we convert 91, 92, 93, 94, 95 is male divorce, female divorce, male single, and so on. So this is for anonymization perspective. And we don't care about the exact value. We care of the classes. This is how machine learning works. Machine learning is not personal. Don't take it personal. Machine learning is about identifying correlation between data. Now, the good thing is that the Machine Learning Studio allows to edit my metadata and add the name of the columns. In this way, it is slightly easier because if I now visualize after editing metadata, I can see the actual name of the column. Okay, so it makes a little bit easier for me that I'm a junior data scientist to see the correlation. For example, I can see a correlation between the amount of credit and I don't know, the personal status. Yeah, why not? So if I see personal status in here, you see we have these 4 bands, 93, 92, 94, and 91, which correspond to this one here. Male, female, divorced, and single. And I can correlate, so I can compare to the credit amount. And now the way you read this is that typically A93, and which A93 is male single, okay? A93 typically borrow between 2,000 and 4,500, with one exception being a peak of nearly 10,000. Okay, so this is how you will read this, and also the other category. So it determines a correlation. Now, this is the manual process. Okay, so I'm doing this correlation field by field, feature by feature. For example, with age. How about age and credit amount? Okay, so you can see the younger people in their 20, 25, 30 typically borrow lower amount of money, 2,000, 4,000. Okay, see there is a a cluster here, and instead older people or elderly people may borrow a little bit more. So you see what's the aggregation. Now, what am I doing? Well, I'm analyzing data. I'm doing the feature engineering, the feature analysis manually because I'm looking this in the screen. A decision tree will do this automatically. So if I look into this, and this probably is going to be not really easy to read because there are so many different branches. So you see there are different branches, and each branch, each bubble here contains some variable. I don't know if this one is visible or not from a distance. Can you see that? Sort of. Okay. So we go and say if you have a saving account, installment, age in years, you have a job, a credit history, duration of the loan in months, and so on. So each bubble is a decision point. On the left, low risk. On the right, high risk. Okay, until you determine the 1 and 2, 1 and 2, 1 and 2. Those are the two classes. This is why it's called a two classes boosted decision tree. But now, because I don't know which one to use, and there are so many that I can use, so this is a classification problem. So you see there are so many different types of machine learning analysis classification that I can do. Now, and if we had the time, I would love to talk about all of them. When to use a forest over a jungle, over a regression, over a perceptron, and so on. So how do I use them? Well, unless you have a very good friend as a data scientist is a very good friend, then it's unlikely that you will know or find out at first try. So just compare them. So here I pick one, a two-classes boosted decision tree, and here I pick the support vector machine. I do exactly the same training, scoring, and then do the evaluation. And then I go and compare them. The one on the left is the score dataset, the blue one. The one on the right is the red one. And then see, hey, how do they compare? Now, in this case, the accuracy is very, very similar. You see, actually, the accuracy is actually the same. So the blue one is 0.738 and the red one is the same. There is a little bit of difference on precision. There is a little bit of difference on recall, on the number of true positive and false not positive, but you see the curve is very much overlapping. So these two way of training the model, they are very, very similar. But sometimes you may get very different result. In that, then you know which one is the best and you will pick that one. Okay, now questions on this other approach. All right, no question in the chat, so let's carry on and go now in the confidential computing case. So why I mentioned these two use cases? These two use cases deal with confidential data. We want to protect and make sure that whoever is running these two services does it with the necessary precautions from a confidentiality perspective. As said, and I'll go quickly on this, confidential computing is not about encrypting data at rest and in transit. We already got that. SQL Server has been encrypting data for years and years. TLS, which is the product, the service being used for HTTPS, has been encrypting data in transit for many years now. What we do in confidential computing is encrypting data when it is in use, exactly when running inside an enclave, a memory space, a region of memory that is put aside by the CPU. So this is hardware encryption, is controlled by the CPU, and the CPU isolate a region of memory where your code, your machine learning code, and your data run in completely isolation from the rest of the application and the rest of the operating system. The hypervisor as well. So that means that not even the cloud provider. So if you're running this in Azure, no one at Microsoft can see what's happening inside an enclave. In theory, it doesn't happen. But in theory, if you're running a traditional virtual machine or a traditional container, someone with the admin password at Microsoft or even within your organization can go sign in inside the VM, take a memory dump, and see what's going on. By running this in a enclave, which is hardware protected at CPU level, each CPU has the encryption key to prevent access to this region of memory by anybody that doesn't have an attestation to access this memory space. Even the cloud provider, even the administrator of the VM or the Kubernetes cluster cannot see what's going on inside the memory space. This is hardware protection in confidential computing using enclaves. And this is actually a memory dump using WinDbg of SQL Server running inside the enclave. I don't see scrambled data. I don't see that at all. I don't see that memory at all. The memory address is like it doesn't exist. The CPU doesn't resolve me, doesn't give me access because I'm not authorized to see data inside the memory space. And I'm going to show you this quickly in SQL Server. SQL Server with two encrypted columns. This is encryption at rest, so nothing fancy in there. It's been around for years now. I'm protecting a social security number and I'm protecting the salary, two confidential pieces of information. Now this is encryption at rest, but as I go into a web application and I build this web application in .NET, ASP.NET, MVC, and I show a list of the employees, what happens is that I have a filter for salary range, I have a filter for social security number, and when I build the query to search, not to filter by salary, by SSN, this query can be intercepted, can be profiled by a middleman. So a SQL profiler actually can intercept, can see what the query looks like, and this query will have a where condition with the social security number, with the salary, so with confidential data. But by running the SQL Server service inside an enclave, the query condition has a search pattern which is encrypted to the eyes of a profiler. So I'm now in a SQL Server profiler, and despite I can see the query itself, I can't see the confidential columns that have been used. They've been encrypted by a special driver that can communicate from the .NET application with SQL Server running inside the enclave, obfuscating or protecting the confidentiality, also parameters in a SQL Server profiler. A typical use case, stay in the financial institution, the financial industry, is to combine machine learning to run inside an enclave and have different banks to share their dataset. Once they have an attestation, so a key to publish, to share the data with the enclave, once the data is inside the enclave, no one can see that data, only the machine learning inside the enclave itself. And now, machine learning benefits of aggregated dataset. So the more data, the better. The increase accuracy of prediction, the increase detection rate, the reduce false positive. And the banks can consume the output of machine learning as a service without risking that confidentiality of the dataset is compromised, because no other banks can access the dataset inside the enclave itself. Questions on confidential computing? I went very quickly because, again, we cover confidential computing in the previous session, and if you didn't have a chance to attend the previous session, we have the recording on the Reactor YouTube channel. So given this context, so given that we have some confidential data, we have some machine learning services, and these machine learning services process confidential data. They do it inside an enclave, so it's all protected. Now, what happens is this is the beauty of the theory, and then we have the real world, right? And the real world is that institutes that are still very traditional, and as I mentioned at the beginning, that even they do horizontal scanning, gut feelings, manually maintain risk tables for their anomaly detection process, for their online payment detection process. So these kind of institutes, traditional institutes, they're very resistant in transferring data, as we have seen here, into an enclave, even if there is the full guarantee of protection in the enclave itself. Say, this is my data. I want to process the data in my data center, in my own secure IT infrastructure, on premises, typically. Fair enough. In this case, federated learning is sort of a second approach or a different approach to still be able to share the trained model for using in machine learning inside the enclave without sharing the initial data source that has generated that trained model. So the centralized learning is the approach that we have seen before. Each bank, each institute, the owner of data, share the data with the machine learning service inside the enclave, and the machine learning service does what we have seen before: take the data, split the data, train the model, score the model. If there are different training approaches, evaluate the model. But this is done in a centralized infrastructure. When there is no trust in the centralized infrastructure, despite confidential computing, federated learning is an approach where each institute can train their model on their own dataset locally, on premises, for example, or in their own private cloud, and then share the trained model with an aggregator of the different trained models, and the trained model produce through the aggregator a global model that doesn't have any reference to the initial data sources and can be used then by machine learning to provide the output that we expect. So still getting the benefit of the aggregation. Now, there are still risks in doing this outside of confidential computing environment, because first of all, in the process of transferring the trained model, attackers can poison the model itself by injecting data, adding data to the trained model that is poison, that is basically not coming from the on-premises training. Or sometimes they can even reverse engineer the trained model and go to the data source that has generated, especially if data sources are not anonymized. This is why the German data source has been anonymized, because we are after classes and not actual data. But if you're not experienced with this process and you train your machine learning model on not anonymized data, it's easier for any attacker to reverse engineer the trained model and recover the data that was used at the very beginning. So in this case, again, confidential computing helps add that level of confidentiality and integrity of your data for two reasons. Confidentiality, as we have already seen before. So you're sharing the trained model, you're not sharing your data, but you're still sharing something that is confidential, your trained model. Not only that, the trained model contains also information about the algorithm that you've been using. So if someone is able to reverse engineer the trained model, can steal your IP, your intellectual property. In this case, IP stands for intellectual property. So the algorithm that you've been using for generating your trained model. There is also a problem of integrity, which is resolved with an attestation. As part of a confidential computing process is the attestation that only the authorized parties, bank 1, 2, 3, 4, and 5 in this consortium, in this circle of trust, are authorized to share trained models, and no one else. So if there is a poisoned data model, the trained model, that doesn't match with checksums or any other way of creating a signature on the model itself, then it can be rejected. It's a validation of code as well. In Azure, we have an open source service called Onyx Inference, confidential Onyx Inference Server, where Onyx or ONNX is a format for sharing machine learning trained model, not the data, but the result of the training. So once the training is done, then you're able to share the trained model inside the enclave, inside the protected area, and apply machine learning on top of that to maintain the security of it. All right, so hope this gets you a few ideas. There is a lot of content here. I totally appreciate. Not easy to digest into one single session. I give you some pointers to deepen your understanding. Start with confidential computing in Azure and reach out to me for any additional follow-up. For Federated Learning, I recommend looking into the Intel OpenFL framework, which is on GitHub, is open source. And for confidential Onyx is on the Microsoft GitHub. Obviously, I said get in touch, not only through the URL in here, but also with me directly, sharing social coordinates, sharing my email address at Microsoft. Happy to get deeper into some specific use cases, sharing slides and source code, and talk to you about addressing these scenarios in your organization using Azure, and as you have seen, using a lot of open source frameworks. Any questions before we close for today?
Thanks, Stefano. If you, we haven't had any questions come through, but if anyone has any, we'll just give you a moment.
Sure.
I'm just going to put up our slide, which will just show you the link to the feedback survey with the event code there. And also I've shared in the Q&A section with you the link to our Reactor upcoming events. For the Sydney page, for anyone else, there is a global page, so you can check out your local one through the global page. And then also the YouTube channel, so that's where we're going to post this in the next 24 to 48 hours. Stefano, did you want to post your links that you have on your slide just in that Q&A section there?
Oh yeah, sure, that's a good idea. Second, that I take them from the slide and I put in there. In the Q&A, right? So I'm gonna go in there, do it like this. Let me see if it comes nicely. There we go. Okay, probably not nicely, but the links are in there. Okay.
Great. Yep, so people just have a moment to copy that. Thank you very much, Stefano, for joining us again today. And thank you everybody for tuning in to another Microsoft Reactor Sydney live stream event. Have a good rest of your afternoon, evening or morning, wherever you've joined us from, and we will see you next time.
Thank you, everybody.
Thanks, Stefano. Bye, everyone.